Hello friends, welcome back to the CSC guy. This is our first lecture of we discussing second chapter in algorithm design and analysis. So let us start with some important points. What is divide and conquer algorithm design? Divide and conquer is an algorithm design paradigm that breaks down a complex problem into smaller subproblems, solves each subproblem recursively, and then combines the solution to the subproblems to solve the original problem. Next, uh, what is let us write an algorithm for control abstraction of divide and conquer. So here, see, this is the divide conquer combine algorithm. In this, input is problem instance. Divide means break down the problem into smaller subproblem. Conquer means recursively solve each subproblem. Combine is combining the solutions to the subproblems to solve the original problem. Now what will be the output? The output will be the solution to the original problem. Next, what is the general recurrence relation for divide and conquer algorithm? The general recurrence relation for divide and conquer algorithm for the given problem t of n is equals to uh, uh, it will be t of n is equals to a t of n by b plus f of n, where a is the number of subproblems, b is the factor by which the problem size is reduced, and f of n is the time complexity of the work done outside the recursive calls. Next, let us see this question. In this, let us solve the recurrence relation using substitution method. The given the given t of n is equal to 1 by t of root n plus c, where n is less than or equal to 4. Here, let us try it by substituting n is equals to 4 and we get t of n t of 4 is equals to 1 by t of 2 plus c. Substituting again, we get t of 2 is equals to 1 by t of 1 plus c. Now we can solve for t of 1 and then substitute back to get the final solution. Next, what is time complexity of binary search with input size n? Let us estimate for n is equals to 100. Time complexity for binary search is big of log n. For n is equals to 100, the time complexity is big of log 100, which is nearly big of 7. Next, what is time complexity of merge sort? Time complexity of merge sort is big of n log n. N log n. Next, let us describe the recurrence relation of merge sort. The recurrence relation for merge sort is t of n is equals to 2t of n by 2 plus big O of n. Next, let us define partitioning element in quicksort. The partitioning element in quicksort is a pivot element that divides the array into two subarrays, one with elements less than the pivot and one with elements greater than the pivot. Next, let us verify the quicksort algorithm takes maximum stack space needed is. Let us verify that if quicksort algorithm takes maximum stack space needed big O of log n. The maximum stack space needed for quicksort is big O of log n, which occurs when the partitioning is always skewed to one side. Next, what is the time complexity of quicksort algorithm? Let us estimate the time if n is equals to 100. The average case time complexity of quicksort is big O of n log n. For n is equals to 1000, the time complexity is big O of 1000 log 1000, which is nearly equal to big O of 10,000. Next, let us solve a recurrence relation which is like this. T of n is equals to t of 1 if n is equals to 1, and t of n is equals to a t of n by b plus f of n if n greater than 1 for the following choices of a, b, f of n and t of 1. First is for a is equals to 1, b is equals to 2, and f of n is equals to cn, and t of 1 is equals to 1. Let us first solve the recurrence relation for this first case. We can solve this recurrence relation using the master theorem. Since a equal to 1, b equal to 2, and f of n is equals to cn, we have t of n is equals to t of n by 2 plus cn. Comparing with the master theorem format, we get t of n is equals to a t of n by b plus f of n tn is equal to 1 into t of n by 2 plus cn. Here a is equals to 1, b is equals to 2, and f of n is equals to cn. Since f of n is equals to cn, which is equal to big O of n, we have f of n is equals to big O of n power d into d, which is equal to 1 into log b, which is equal to log 2, which is therefore equal to 1. Since d is equal to 1, which is equal to log b, we can apply the master theorem. So t of n will become t of n is equals to theta of n power d log kn into t of n, which is equal to theta of n power 1 log of n t power n t of n, which is equal to theta of n. Now let us see the second case, in which a is equal to 5, b is equal to 4, f of n is equals to cn square, and t of 1 is equals to 2. We can solve this recurrence relation using the master theorem. Since a equal to 5, b is equals to 4, f of n is equals to cn square, we have t of n is equals to 5t of n by 4 plus cn square. Comparing with the master theorem format, we get t of n is equals to a t of n by b plus f of n into t of n, which is equal to 5t of n by 4 plus cn square. A is equals to 5, b is equals to 4, and f of n is equals to cn square, which is equal to big O of n square. We have f of n is equals to big O of n power d into d, which is equals to 2 log b, which is equal to log 4 equal to 2. Since d is equals to 2, which is greater than log b, we can apply the master theorem. T of n is equals to theta n power d into t of n, which is equal to theta of n square. Next, let us explain detecting a counterfeit coin from a set of n greater than 1 coins using divide and conquer methodology. How many weight comparisons are done? The problem of detecting a counterfeit coin from a set of n coins can be solved using the divide and conquer methodology. First, let us see the algorithm. Divide the set of n coins into two subsets of approximately n by 2 coins each. Now, let's next weigh the two subsets against each other. If one subset is heavier, repeat the process with that subset. If the two subsets are balanced, the counterfeit coin is in the other subset. Repeat the process with that subset. Continue the process until you have only one coin left, which is the counterfeit coin. Now, what is the time complexity? The time complexity of this algorithm is big O of log n, since we divide the problem size by 2 in each iteration. Number of weighted comparisons. The number of weighted comparisons done is log of n, since we need log n iteration to reduce the problem size from n to 1. Next, let us write an algorithm for recursive and iterative versions of binary search with data size n and estimate the time complexity of the algorithms. So see, this is the recursive binary search algorithm. In this, we use an input array A, target element x, low and high. If high is less than low, then we will return -1, which means element not found. Next, we assign mid value with low plus high by 2. If a of mid is equal to x, we return mid, which means element found. If a of mid is less than x, we return recursive binary search. Again we recurse it with a x mid plus 1 and high. Else we recurse the method with a x low mid minus 1. Next, iterative binary search algorithm. In this, input is array A, target element x. We define low and assign it with 0, high with n minus 1. While low is less than or equal to high, mid value will be low plus high by 2. If a of mid is equal to x, we return mid, which means element is found. If a of mid is less than x, low is equals to mid plus 1. Else high is equal to mid minus 1, and we return minus 1, which means element not found. The time complexity of both the recursive and iterative binary search algorithm is big O of log n, since we divide the search space by 2 in each iterations. Thank you.